Okay, this is 5.3. We're going to talk about proving triangle congruence by something called SAS. We'll explain that here in a minute. Essential question is, what can you conclude about two triangles when you know that two pairs of corresponding sides and the corresponding included angles are congruent? Core vocabulary things that this is kind of a review. Congruent figures and rigid motion. We've talked about those before. What you're expected to learn, we're going to use the SAS, which is the side angle side congruence theorem, to talk about triangles. So let's get started. We're going to start by defining congruent figures. That's just simply geometric figures that have the same size and shape. Okay, we've talked about this before. That just means that the corresponding angles are congruent and the corresponding sides are congruent. Alright, so this whole lesson is pretty much just talking about this one theorem, the side angle side, or SAS theorem. And it just says that if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. Okay, so I'm going to kind of explain some things, or explain this, and then I want to look at really what this word means right here, this included angle. That's going to be important. So I'm going to start by drawing some triangles. Alright, so if I got a triangle here, and then I have another triangle beside it, and let's just call this A, B, and C. If I call this one D, E, and F. And I'm just going to pick two sides of this first triangle, A, B, C. And let's say that I pick this side with this side. Okay. The included angle is the angle that connects these two sides. If I kind of go from C and B and I see where they intersect, these two lines intersect at A. So this right here, that's going to be my included angle. Okay. It's included because it shares them. So if I look at this other triangle DEF, and I say, let's say that DE is congruent to AB and AC is congruent to DF, right? That other included angle has to connect E and F, and it does at D. Right. So I don't have to show that all three corresponding angle pairs, and all three corresponding side pairs are equal. I can kind of take a shortcut, and this theorem just says that I only need two pairs of sides and one angle. The thing that makes a difference is this included angle. That angle has to kind of be sandwiched between the two sides that I'm saying are congruent. So if that's the case, I have my two corresponding sides that are congruent, my two pairs of corresponding sides, and my pair of included angles that are congruent. Then I can say that triangle ABC is congruent to triangle DEF. Okay? That would be our SAS, or side angle side theorem. Alright, here's example number one. We have to do proofs on this. We're given that segment BC is congruent to segment DA, and segment BC is parallel to segment AD. And we want to show that triangle ABC is congruent to triangle CDA. So I have a triangle ABC here on top, and then down here, kind of flipped over, is CDA. All right? And I want to show that these two triangle pieces are congruent. And the theorem that we want to use, of course, based on this lesson, is the SAS theorem. All right? Now remember that means that I have a side, an angle, and a side. And the angle has to be included between the two sides. So, we always start with our givens. So here's my given information. I know that segment BC is congruent to segment DA. And I also know that segment BC is parallel to segment AD. My reason is that it's given. Okay. Now this segment BC is congruent to segment DA. That's going to be one of my sides. So So I have the S part, one of the S's. Okay. Now I have to look at getting the angle, the included angle, and the other side pair. Now, this parallel is important because if you remember, if I have two parallel lines cut by a transversal, there's some things that happen. One of them is that I have these alternate interior angles that are congruent. So because BC is parallel to AD, I'm going to know that this angle here is congruent to this angle here. Okay, so that's going to be my included angle. We have to call this out. So this is angle BCA is congruent to angle DAC. And the reason I can say that, that's going to be the alternate interior angles theorem. Okay, so there's my A. Okay, now I need another side. There's nothing that tells me that this side is congruent to this side. I don't have any information that I can conclude that from. But I do have two triangles that share this side. I can kind of pull them apart, and AC, this segment here in the middle, would be a part of both of those triangles. So I can say that AC is congruent to segment AC. That is going to be called the reflexive property, right, of congruence. Okay. And that gives me, if you will, my second pair of sides. So that would be my SAS, my side angle side. Okay, so now that I have my three corresponding pairs that are congruent, I can say triangle ABC is congruent to triangle CDA. And the theorem would be the side angle side theorem. Alright, in this next example, it says in the diagram segment QS and segment RP pass through the center of M, or center M of the circle, and it wants us to conclude something about the triangle MRS and triangle MPQ. Okay. Because of that, because it's in the center, the circle, that means that these radii are all going to be congruent. So in particular, I want MR congruent to these other segments. All right. So there's my two side pairs. I know all my radii are congruent. Because this line RP, or this line segment RP, and this line segment QS, they intersect. Remember that I have vertical angles here. So that means this angle is congruent to that angle. Okay. Which then means that I have my side angle side. Because this side here touches this angle M, and from here, Q and P, they intersect at M. So these two are my included angles. So that side angle side. So what can I conclude? I can actually say that triangle MRS is congruent to triangle MPQ, and that would be by my side angle side theorem. Okay? Because we were able to come up with two sets of corresponding sides that are congruent, and the included angle is congruent to both triangles, or in both triangles. So this would be my answer. Alright, example number 3. We're given two statements that segment JN is congruent to segment MN, segment NK is congruent to segment NL. And I want to show that two triangles JNK and MNL are congruent. Now, the two triangles that we're talking about goes JNK and K. And then I want to look at that one compared to this triangle MNL, which is out here. All right, so I'm looking at those two triangles. And I want to show how those two things are congruent to each other. All right, so let's go ahead and write down our givens. I have Jn is congruent to Mn. And then I also know that Nk is congruent to Nl. And both of those are given. Okay. Now I need a included angle. So if I look at those two segments, on both of them, they kind of converge, they connect at this point in here. So I somehow need to show that this angle here is congruent to that angle there. I know I can do that because I have two lines. I have Km intersecting that line JL, and so I know that angle JNK is congruent to angle MNL because of the vertical angles theorem. Anytime I have vertical angles, those angles are congruent. So here's my side, and angle, or my side, angle, side. Since the angle's got to be included, it's got to be in between them, in between the two corresponding sides. So I have my three pairs. Now I can say that triangle JNK is congruent to triangle MNL because of the side, angle, side theorem. Okay. So there you go. We have this proved. All right, here's example number 4. If you have the notes, it has a bigger piece that looks like a quilt. It says on the instructions. I just kind of condensed that with my given statement and my prove, and I drew the picture of the piece that I needed. So here we go. Let's go ahead and get this proved. I know that segment PS is parallel to segment QR. So my reason is given. I'm also told that PS is congruent to QR, and that's given. Okay, so I'm going to go ahead and mark this on my drawing so that I can see what I have. I know that this side is parallel to this one, and I also know that they're congruent to each other. All right, I want to show that PQR is congruent to RSP. I have one pair of sides. I'm going to have to use this theorem about the congruency. Remember, or not congruency, parallel. If I have parallel lines, that means connect or intersected by a transversal. I'm going to have a pair of alternate interior angles that are congruent. So that's what we're going to write. I'm going to know that angle SPR is congruent to angle QRP. Okay, and that is the alternate interior angles theorem. Okay, so I have a side angle. I need my third side, or my second side. Right? If I'm looking at this where that angle connects, I'm looking at this segment PR, which is here. And I know it's congruent to itself because of the reflexive theorem. So I'm going to, or reflexive property. So I know segment PR is congruent to segment RP. That would be the reflexive property. Okay, and so there's my side, my included angle, and my side. So now I can make this statement that triangle PQR is congruent to triangle RSP because of the side, angle, side theorem. Okay. So there it goes. I know this triangle is congruent to this triangle because of my side, angle, side.